The heat is flowing through two cylindrical rods of same material. The diameters of the rods are in the ratio 1:2 and their lengths are in the ratio 2:1. If the temperature difference between their ends is the same, the ratio of rate of flow of heat through them will be, the options given are 1:1, 1:4, 2:1 and 1:8. Now, since they've asked the rate of heat flow, so that is nothing but Q by T, and we know that Q by T can be given by K A delta theta, or the change in temperature, upon the length of the rod. Now in this question they've given that the material is same, so K would be constant. Also the temperature difference across both the rods is same, so delta theta or d theta is the same or is constant. So therefore Q by T is proportional to A by L, and A is nothing but area of cross section, that is pi by 4 d square. So we can write A is proportional to d square upon L. So now Q by T for the first case would be equals to, or would be proportional to d1 square upon L1. Similarly for the second case, Q by T would be proportional to d2 square upon L2. So Q by T for the first case upon Q by T for the second case, the ratio comes out to be d1 upon d2 squared times L2 upon L1. Now the ratio of the diameters is given as 1:2. So 1:2 squared, and the ratio of the lengths is given as 2:1. So that is 2:1, L1 upon L2. So this is 1 by 4 times 1 by 2, which comes out as 1 by 8. Hence option D, 1 by 8, is the correct answer. The ratio of thermal conductivity of two rods of different material is 5:4. The two rods are of same area of cross section and same thermal resistance will have the lengths in the ratio. The options given are 4:5, 9:1, 1:9 and 5:4. Now we know that the resistance, thermal resistance, can be given by L upon K times A. So for the first case, R1 is L1 upon K1 times A1. Similarly for R2, it is L2 upon K2 times A2. Now R1 and R2 have to be equal, since that's what we need to find out, same thermal resistance. So therefore let's equate L1 upon K1 A1 would be equals to L2 upon K2 times A2. Now we given that the area or cross sectional areas are the same, so these gets cancelled out. So what we are left with is L1 upon L2 would be equal to K1 upon K2. So K1 upon K2 is in the ratio of 5:4. So L1 upon L2 would also be in the ratio of 5:4. Hence option D is the correct answer. Which of the following circular rods, given radius r and length L, each made of the same material and whose ends are maintained at the same temperature, will conduct most heats? The options given are r is equals to 2 times r naught and L is equals to 2 times L naught. R is equals to 2 times r naught and L is equals to L naught. The radius r is equals to r naught and length L is equals to L naught. And the last option is R is equals to R naught and L is equals to 2 times L naught. Now, the formula for rate of conduction of heat, Q by T, is given by K times the area of cross section times the temperature difference upon the length of the rod. Now, from the question, as we know, the the rods are made of same material and the temperatures across the ends are maintained equal. So therefore K and delta theta are constants. So Q by T is proportional to A by L, which can be said to be proportional to d square by L, that is nothing but proportional to r square by L. So basically the rod which has the highest ratio of r square by L would be conducting most amount of heat. Now from the given options, let's check the ratio of r square by L. So for the first option, r square is 2 times r naught square upon 2 times L naught. So that would be 2 r naught upon L naught. For the second option, it's 2 r naught square upon L naught. So that is 4 r naught square upon L naught. For the third case, it is r naught squared upon L naught. So that is the same. And for the fourth case, it is r naught square upon 2 times L naught. So that is 2 times L naught. Now from these four options, we can see that the highest value is for B, hence option B is the correct answer. Two walls of thickness D1 and D2 and thermal conductivities K1 and K2 are in the contact. In steady state, if the temperatures at the outer surface are T1 and T2, the temperature at the common wall is, the options given are K1 T1 D2 plus K2 T2 D1 upon K1 D2 plus K2 D1, K1 T1 plus K2 D2 upon D1 plus D2. The third option is K1 D1 plus K2 D2 upon T1 plus T2, the whole thing multiplied by T1 times T2. And the last option is K1 D1 T1 plus K2 D2 T2 upon K1 D1 plus K2 D2. Now, the rate of heat flow dq by dt, as we know, is given by k times a into delta theta upon d, or the length. Now let's just draw a schematic of this problem. So let's say these are the two walls, and d1 and d2, let d1 and d2 be the thickness of the walls. Now the area of cross section of the walls is same. Let T1 be the temperature on this side of the wall, T2 be the temperature on the other end, and let theta be the common temperature at the interface. And the conductivity of this wall is K1 and of this is K2. So now, since as we can see, when heat flows in this direction, the total amount of heat flowing, because this is a series combination, the total amount of heat flowing would be the same. So therefore dq upon dt is equals to k1 a1 times t1 minus theta, since this would be at a higher temperature and this would be at an intermediate lower temperature, upon d1, and this would also be equal to k2 times a2 into theta minus t2 upon d2. However, since the areas of cross section are equal, so an a1 and a2 get cancelled out. So what we are left with is k1 times t1 minus theta upon d1 is equals to k2 times theta minus t2 upon d2. So solving this, we get k1 d2 t1 minus theta is equals to k2 d1 theta minus t2. So simplifying this, we get k1 d2 t1 minus k1 d2 theta is equals to k2 d1 theta minus k2 d1 t2. Now solving further, we'll need to isolate this theta term, since we want to find out the temperature at the common wall, which is nothing but theta. So isolating theta, we get theta is equals to k1 d2 t1 plus k2 d1 t2 upon K1 D2 plus K2 D1. Now this is matching with option A, hence option A is the correct answer. A cylindrical rod having temperature T1 and T2 at its ends, the rate of flow of heat is Q1 calories per second. If all the linear dimensions is doubled, keeping the temperature constant, then rate of flow of heat Q2 will be, the options given are 4 times Q1, 2 times Q1, Q1 by 4 and Q1 by 2. Now the rate of flow of heat is given as Q1, and which is nothing but K times the area of cross section into the temperature difference across the ends upon the length of the rod. So this is for the first case, so it would be K1 A1 L1. Similarly for the second case, Q2 is K2 A2 delta theta upon L2. Now since it is the same rod, therefore the material doesn't change. So let's just write Q1 upon Q2 would be equals to A1 delta theta upon L1 times K2 A2 delta theta upon L2. Now the material is same, so K1 and K2 gets cancelled out. Also the temperature difference across the ends isn't changed, so delta theta also gets cancelled out. So what we are left with is A1 upon A2 into L1 upon L2. Now in this A is the area of cross section, so that can be written as R1 squared or pi R1 squared upon pi R2 squared. The pi gets cancelled times L2 upon L1. Now it's given that all the linear dimensions are doubled. So R2 would be 2 times R1. So R1 squared upon 2 times R1 squared into L2 would become 2 times L1. So L1 upon 2 times L1 upon L1. So what we are left with is R1 squared upon 4 times R1 squared into 2 times L1 upon L1. So these get cancelled out. So what we are left is 1 by 2. Q1 by Q2 is equals to 1 by 2. So Q2 is equals to 2 times Q1. So hence option B is the correct answer. If two metallic plates of equal thickness and thermal conductivities K1 and K2 are put together face to face and a common plate is constructed, then the equivalent thermal conductivity of this plate will be, the options given are K1 K2 upon K1 plus K2, K2 times K1 K2 upon K1 plus K2, K1 square plus K2 square the whole raised to 3 by 2 upon K1 K2, and the last option is K1 square plus K2 square upon 2 times K1 K2 and raised to 3 by 2. Now as we can see in the schematic, this K1 and K2, these two plates form a series combination, and in series combination the equivalent resistance adds up, so it would be R1 plus R2. Now the formula for thermal resistance can be given as 2L1 or 2L upon K equivalent times the area of cross section would be equal to L upon K1 into A1 plus L upon K2 into A2, but A1 and A2 or they have the same area of cross section, only change is the thermal conductivity, therefore K1 and K2. And this 2L1, 2L is nothing but the sum of both the lengths L and L. So therefore, simplifying this, we get 2 times K equivalent is equals to 1 upon K1 plus 1 upon K2, since A and L are the same. So therefore, what we are left with is K equivalent is equals to 2 times K1 K2 upon K1 plus K2. Hence, option B is the correct answer. Two spheres of different materials, one with the double the radius and 1/4 wall thickness of the other, are filled with ice. If the time taken for complete melting of the ice in the large radius one is 25 minutes and that for the smaller one is 16 minutes, the ratio of thermal conductivities of the materials of large sphere to the smaller sphere is, the options given are 4 is to 5, 5 is to 4, 25 is to 1 and 1 is to 25. Now, as we know, Q by T is equals to K times A into delta theta upon the thickness or length in this case. So, since both the spheres are filled with ice, so the amount of heat that would need to be taken out is the same for both the spheres, and the temperature inside both the spheres would be 0 degrees Celsius and outside would be ambient temperature, that would be something like 24-25 degrees Celsius. So delta theta is also the same for both the spheres. So therefore Q and delta theta are constants. So we can write this equation as K is proportional to 1 by A times T. So that is nothing but it's proportional to 1 upon R square into T. Pardon me, this would be L. So L upon A times T, and that can be proportional to L upon R square times T. So therefore, for the thermal conductivity of larger upon the thermal conductivity of the smaller sphere would be equal to L1 upon or L large upon L small times R small upon R large squared times the time of melting for small divided by the time of melting for large. Now it is given that R1 has twice the thickness of the smaller sphere and the wall thickness is 1/4 that of the smaller sphere. Also, the time for the larger sphere is 25 minutes and that for the smaller sphere is 16 minutes. So substituting these values, we get K large upon K small is equals to 1 by 4 into 1 by 2 squared times 16 by 25. So this value is nothing but 1 by 25. So therefore the value of K large is to K small is 1 is to 25. Hence option D is the correct answer. The coefficient of thermal conductivity of copper is 9 times that of steel in the composite cylindrical bar as shown in the figure. What will be the temperature at the junction of the copper and steel? The options given are 75 degrees Celsius, 67 degrees Celsius, 25 degrees Celsius and 33 degrees Celsius. Now, as we know, since both these rods form a series combination, so therefore in the previously we have found out the value of a junction temperature, which is theta is equals to K1 T1 times L2 plus K2 into T2 times L1 upon K1 L2 plus K2 L1. In that case L was replaced by D. Similarly, for this case, since lead copper or conductivity of copper is given as 9 times conductivity of steel. So if we assume that the thermal conductivity of steel to be K1, so thermal conductivity of copper would be 9 times K1. So substituting these values, we'll get the value of theta is equals to 9. We will get it as 9K plus let this be equals to k, so this would be equal to 9k. So 9k times 100 into 6 plus k times 0 into 18 upon 9k into 6 plus k into 18. So solving this, we get 5400 k upon 72k. So these k's gets cancelled out, and what we are left with is 75 degrees Celsius. Hence option A is the correct answer. A metal plate 4 mm thick has a temperature difference of 32 degrees Celsius between its faces. It transmits 200 kilocalories per hour through an area of 5 centimeters square. Thermal conductivity of the material is, the options given are 58.33 watt per meter degree Celsius, 33.58 watt per meter degree Celsius, 5 into 10 raised to minus 4 watt per meter degree Celsius, and the last option is none of these. Here the thickness of the plate, let's call it as delta x, is given as 4 mm. So that is nothing but converting into standard units, we get 4 into 10 raised to minus 3 meters, and the temperature difference delta T is given as 32 degrees Celsius. So they transmit, so delta Q by delta T would be nothing but is given as, it transmits 200 kilocalorie per hour. So let's convert this into joules per second. So that is 200 into 1000, this becomes calories, and 1 calorie is 4.2 joules. So multiply it by 4.2 upon the hours can be written as 60 minutes into 60 seconds. So this value comes to 233.33 joules per second. Now this is a standard SI unit value. Also the area of cross section is given as 5 centimeters square, which is nothing but 5 into 10 raised to minus 4 meters squared. Now the general formula delta Q by delta T is equals to K times A into delta capital T, change in temperature, upon the thickness. So therefore the value for thermal conductivity K can be given as delta Q by delta T upon A into delta of capital T divided by delta X. So K would be nothing but 233.33 into 10 raised to minus 3 upon into 4. This 4 into 10 raised to minus 3 is nothing but the thickness, and area A is 5 into 10 raised to minus 4, and the temperature difference is given as 32. So on solving this, we get the value as 58.33 watt per meter degrees Celsius. Hence option A is the correct answer. Which of the following statements is correct? Let's look at each of the statements. The first statement says a good absorber is a bad emitter. As we know, this is a commonly known fact that a good absorber is a good emitter. So hence option A is incorrect. Now the second statement says that every body absorbs and emits radiation at every temperature. This is somewhat correct. Every body absorbs and emits radiation from the surrounding at every temperature, but it stops at 0 Kelvin. So not at every temperature does the object absorb and emit. Only for 0 degrees Kelvin or 0 Kelvin, the body does not absorb or emit any kind of radiation. So the every temperature word is incorrect. Hence option B is incorrect. The third option says that the energy of radiation emitted from a black body is same for all wavelengths. Now, according to Stephen's law, energy emitted is proportional to the fourth power, and according to Wien's law, we know that the lambda or wavelength is inversely proportional to the temperature. So, energy is basically inversely proportional to fourth power of the lambda. So, it's not the same for every wavelength. Hence, option C is also incorrect. Now the option D, the law showing that the relation of the temperature with wavelength of maximum emission from an ideal black body is Planck's law. Now Planck's law shows the relation between the uh, wavelength and the temperature, like energy emitted for a particular wavelength is equals to 8 pi hc upon lambda raised to 5 times 1 upon e raised to hc by kt minus 1 into d for the same lambda. So as you can see, this is the Planck's law and it relates wavelength or the energy with temperature T. So therefore option D is correct answer. If the wavelength of maximum intensity of radiation emitted by the sun and the moon are 0.5 into 10 raised to minus 6 meters and 10 raised to minus 4 meter respectively, the ratio of their temperatures is, the options given are 1 is to 100, 1 is to 200, 100 and 200. Now according to Wien's law, the maximum wavelength lambda m times the temperature is a constant. So let T1 be the temperature of the sun and T2 be the temperature of the moon. So T1 by T2 is equals to lambda 2 upon lambda 1. So that is given as T1 upon T2 is equals to 10 raised to minus 4 upon 0.5 into 10 raised to minus 6. So this value comes out to be 200. Hence option D is the correct answer. The wavelength of maximum energy released during an atomic explosion is 2.93 into 10 raised to minus 10 meters. Given that Wien's constant is 2.93 into 10 raised to minus 3 meter Kelvin, the maximum temperature attained must be of the order of, the options given are 10 raised to minus 7 Kelvin, 10 raised to 7 Kelvin, 10 raised to minus 13 Kelvin, and 5.86 into 10 raised to 7 Kelvin. Now, according to Wien's law, uh, temperature is given by B upon lambda m, where B is nothing but the Wien's constant. So, substituting the values, we have been given that 2.93 into 10 raised to minus 3 upon 2.93 into 10 raised to minus 10. So on simplifying, we get as 10 raised to 7 Kelvin. So temperature would be of the order of 10 raised to 7 Kelvin. Hence option B is the correct answer. The radiation density per unit wavelength at a temperature T has a maximum at a wavelength lambda naught. At temperature 2T, it will have a maximum at a wavelength. The options given are 4 times lambda naught, 2 times lambda naught by 2 and lambda naught by 4. Now, for temperature T, the maximum wavelength is lambda naught, and for T naught, 2 times T, we need to find out what would be the maximum. According to Wien's law, we know that T times lambda is equals to a constant. So therefore, lambda naught into T would be equal to, let's call this unknown as lambda dash. So lambda dash times 2T. So solving this, we get lambda dash is equals to lambda naught upon 2. So therefore option C is the correct answer. A metal ball of surface area 200 centimeters square and temperature of 527 degrees Celsius is surrounded by a vessel at 27 degrees Celsius. If the emissivity of the metal is 0.4, then the rate of loss of heat from the ball is, the value of sigma is given as 5.67 into 10 raised to minus 8 joule per meter square second Kelvin raised to 4. The options are 108 joules approx, 168 joules, 182 joules and 192 joules. Now the rate of heat loss E is given by sigma E A times T raised to 4 minus T naught raised to 4. Since the ball is not a perfectly black body, it will have an emissivity, and this T is the temperature of the ball and the T naught is the temperature of the surroundings. So the value of sigma is given as 5.67 into 10 raised to minus 8 times E is nothing but 0.4. The surface area is given as 200 centimeters squared. So converting into meter squared, we will get as 10 raised to minus 4 times the T is given as 527 degrees Celsius. So converting it into Kelvin, we will get 527 plus 273 raised to 4 minus the temperature of the surrounding is given as 27 degrees Celsius. So 27 plus 273 in Kelvin, the whole thing raised to 4 again. So solving this, we get 5.67 into 10 raised to minus 8 times 0.4 into 200 into 10 raised to minus 4 into 800 raised to 4 minus 300 raised to 4. So when we solve this, we get the value of this as 182 joules per second. Hence option C is the correct answer. In MKS system, Stefan's constant is denoted by sigma. In CGS system, the multiplying factor of sigma will be, the options given are 1, 10 raised to 3, 10 raised to 5 and 10 raised to 2. Now in MKS system, the value of sigma, the unit of sigma is nothing but joule per meter square second into Kelvin raised to 4. So this is the unit in MKS system. So 1 joule is nothing but 10 raised to 7 ergs. So this is the CGS form, and MKS system 1 meter square can be written as 10 raised to 4 centimeters square, and the second is the same in both the systems, and the temperature is also Kelvin in both the systems. So what we are left with is joule per meter square Celsius Kelvin raised to 4 would be this 10 raised to 4 and 10 raised to 7 can be written as 10 raised to 3 erg per centimeter square second into Kelvin raised to 4. So the multiplying factor is 10 raised to 3. Hence option B is the correct answer. The tungsten filament of an electric lamp has a surface area A and a power rating of P. If the emissivity of the filament is epsilon and sigma is the Stefan's constant, the steady temperature of the filament will be, the options given are T is equals to P upon A epsilon sigma raised to 4, T is equals to P upon A epsilon sigma, T is equals to A epsilon sigma upon P, the whole thing raised to 1 by 4, and T is equals to P upon A epsilon sigma, the whole thing raised to 1 by 4. Now the power P is nothing but rate of heat flow, that is Q by T, and this Q by T is given as A epsilon sigma T raised to 4. So therefore power is equals to A epsilon sigma T raised to 4. Now isolating the value of T, so we get T raised to 4 is equals to P upon A epsilon times sigma. So therefore the value of T would be the fourth root of P upon A epsilon sigma. So hence option D is the correct answer. A steel square plate with each side equal to 10 centimeters is heated by a blacksmith. The rate of radiated energy by the heated plate is 1134 watt. The temperature of the hot steel plate is, this value of Stefan's constant is given as 5.67 into 10 raised to minus 8 watt per meter square per Kelvin raised to 4. Emissivity of the plate is given as 1. The options are 1000 Kelvin, 1189 Kelvin, 2000 Kelvin and 2378 Kelvin. Now, the power is given as 1134 watt, and power is nothing but rate of emission, that is Q by T, and Q by T is A times epsilon sigma T raised to 4. So equating these two, we get 1134 is equals to A times epsilon into sigma T raised to 4. Now the emissivity is given as 1, so epsilon is 1. So 1134 is equals to A is, since it's a square plate, so the surface area would be length into breadth. So 10 centimeters can be written as 0.1 meter. So 0.1 squared times epsilon is 1. The value of Stephen's constant is given as 5.67 into 10 raised to minus 8 watt into T raised to 4. So to find out the value of temperature T raised to 4, we get 1134 upon 0.1 squared into 5.67 into 10 raised to minus 8. So solving this, we get the value of temperature as 1189 Kelvin, hence option B is the correct answer. The energy spectrum of a black body exhibits a maximum around a wavelength of lambda naught. The temperature of the black body is now changed such that the energy is maximum around a wavelength of 3 lambda by 4. The power radiated by the black body will now be increased by a factor of, the options given are 256 by 81, 64 by 27, 16 by 9 and 4 by 3. Now, according to Wien's law, we know that lambda m, or maximum wavelength, times the temperature is constant. So therefore, lambda max for the first case times first temperature is equals to lambda max for the second case. So the second temperature, or temperature in the second case T2, is equals to T1 times lambda m1 upon lambda m2, that is nothing but T1 upon lambda naught upon 3 lambda naught upon 4. So therefore T2 is equals to 4 upon 3 times T1. Now the power is given by A epsilon sigma T raised to 4. So since it is the same object, so we can say power is proportional to temperature raised to 4. So therefore P2 upon T1 is nothing but T2 upon T1 raised to 4. So P2 upon T1 is, T2 is nothing but 4 by 3 times T1. So 4 by 3 T1 upon T1 raised to 4. So T1 gets cancelled. So what we are left with is 256 upon 81. Hence option A is the correct answer. Two identical objects A and B are at temperatures TA and TB respectively. Both objects are placed in a room with perfectly absorbing walls maintained at temperature T such that TA is greater than T and which is greater than TB. The objects A and B attain the temperature T eventually. Which of the following statements is correct? Let's look at the statements. The first statement says that A only emits a radiation while B absorbs radiation until both attain the temperature. The second statement says that A loses more radiation than it absorbs while B absorbs more radiations than it emits until temperature T is attained. The third option says that both A and B only absorb radiation until they attain temperature T. And the last option says that both A and B only emit radiations until they attain the temperature T. Now, according to Prevost's theory, every object emits as well as absorbs radiations at all temperatures except at 0 Kelvin. So therefore, the statements which say that A and B only absorb or A and B only emit, these both statements have to be wrong, because every body absorbs as well as emits both radiations at all temperatures except at 0 Kelvin. Now look at the first statement. It says A only emits radiation while B only absorbs radiation. So this is also incorrect. So therefore, since temperature of A is greater than the common temperature, so A would be emitting more amount of radiation as compared to what it absorbs. Similarly, temperature of B is smaller than the average temperature, so B would be absorbing more radiation than it would be emitting. So that is what is stated in the second statement. A loses more radiation than it absorbs, while B absorbs more radiation than it emits until the temperature T is attained. Hence option B is the correct answer. Three very large plates of same area are kept parallel and close to each other. They are considered as ideal black surfaces and have a very high thermal conductivity. The first and the third plates are maintained at temperatures 3T and 2T respectively. The temperature of the middle plate, that is the second plate, under steady state condition is, the options given are 65 by 2 raised to 1 by 4 T, 97 by 4 the whole raised to 1 by 4 t, 97 by 2 the whole raised to 4 1 by 4 times t, and 1 by 97 raised to 4 times t. Now let's look at the schematic. This is the first plate, the middle plate, and the third plate. So the first plate is at temperature 3T. Let's assume that the middle plate is at a temperature T dash and the last plate is at a temperature T. So at the steady state condition, for steady state condition, the energy absorbed by the middle plate would be equal to the energy emitted by the middle plate. So therefore 3 sigma times A into 3T raised to 4 minus, this is the energy absorbed from the first to the second plate, and sigma times A into T dash raised to 4, this is the energy emitted from the middle plate, and this would be equal to sigma A T dash raised to 4 minus sigma A, this is the energy absorbed from the third plate to the second one, is equals to 2 times T raised to 4. So on simplifying this, we get 3T raised to 4 minus T dash raised to 4 is equals to T dash raised to 4 minus 2T raised to 4. So simplifying this, we get 2T dash raised to 4 is equals to 16 plus 81 T raised to 4. So therefore T dash is equals to 97 upon 2 the whole raised to 1 by 4 times T. Hence option C is the correct answer. Two spheres of radii in the ratio 1:2 and the densities in the ratio 2:1 and of the same specific heat are heated to the same temperature and left in the same surrounding. Their rate of cooling will be in the ratio, the options given are 2:1, 1:1, 1:2 and 1:4. Now the formula for rate of cooling is nothing but Q by T is given by mc delta theta upon T. Now mass is nothing but density times volume. So mass of the sphere, we can write it as density times volume is 4 by 3 pi r cube. So mass per unit area, so that will be mass per unit area is nothing but 4 upon 3 pi r cube times rho upon 4 pi r square. So this comes out as 1 by 3 r into rho. So as we can see, the rate of cooling per unit area is proportional to, so rate of cooling per unit area is proportional to 1 by 3 times r into rho. So the ratio of rate of cooling for both the spheres, so let's say q1 upon q2 would be equal to r1 rho 1 upon r2 rho 2. Now r1 is to r2 is given as 1 is to 2, and rho 1 is to rho 2 is given as 2 is to 1. So therefore q1 by q2 is nothing but 1 by 2 times 2 by 1, so that is 1 is to 1, hence option B is the correct answer. A body takes 5 minutes to cool from 90 degrees Celsius to 60 degrees Celsius. If the temperature of the surroundings is 20 degrees Celsius, the time taken by it to cool from 60 degrees Celsius to 30 degrees Celsius will be, the options given are 5 minutes, 8 minutes, 11 minutes and 12 minutes. Now, in order to solve this, we need to use the Newton's law of cooling. So which says that for the first case, the temperature difference 90 minus 60 upon time taken, that is 5 minutes, is equals to the Newton's cooling constant into 90 plus 60 upon 2. This is the average temperature minus temperature of the surrounding, which is 20 degrees Celsius. So therefore 6 is equals to K times 55. So the value of K, or Newton's cooling constant, is 6 upon 55. Similarly, for the second case, the temperature is now from 60 to 30. Let's say in a time t, this would be equal to 6 upon 55 times the average temperature, that is 60 plus 30 upon 2 minus the temperature of the surrounding, that is 20 degrees. So on solving this, we get the value of t as 11 minute, hence option C is the correct answer. A calorimeter of mass 0.2 kg and specific heat 900 joule per kg Kelvin containing 0.5 kg of a liquid of specific heat 2400 joule per kg Kelvin, its temperature falls from 60 degrees Celsius to 55 degrees Celsius in 1 minute. The rate of cooling is, now options given are 5 joules per second, 15 joules per second, 100 joules per second and 115 joules per second. Now in this case, the rate of cooling is nothing but the loss of heat. So dq by dt is given by mc delta theta upon delta t. Now as we know, heat is lost by the calorimeter as well as the liquid. So therefore dq by dt would be m, or mass of liquid, into specific heat of liquid plus mass of the calorimeter into specific heat of calorimeter times the temperature difference delta theta upon delta T. So mass of liquid is 0.5 and a specific heat of 2400 plus mass of the calorimeter is 0.2 times the specific heat of 900. This multiplied by the temperature difference is 60 to 55, so that is 5 upon time is 1 minute, that can be written as 60 seconds. So on solving this, we get the value as 115 joules per second, hence option D is the correct answer. Two rods, one semicircular and other straight, of the same material and of the same cross-sectional area, are joined as shown in the figure. The points A and B are maintained at different temperature. The ratio of heat transferred through a cross-section of the semicircular rod to the heat transferred through the cross-section of the straight rod in a given time is, the options given are 2 is to pi, 1 is to 2 pi is to 2 and 3 is to 2. Now the rate of heat transfer dq by dt is given by k times A into delta theta upon the length of the uh, rod. Now in this case, since the material is the same and area of cross section is given as equal, also A and B are constants, or the temperature difference across the ends are constant for both straight and semicircular rods. So K, A and delta theta are the constants for both the cases. So dq by dt for the semicircular rod uh, is nothing but 1 by L, or is proportional to 1 by L of the semicircular rod. Similarly, dq by dt for the straight rod is also inversely proportional to the length of the straight rod. So let's take a ratio of this. So dq by dt for semicircular upon dq by dt for the straight would be length of the straight upon length of the semicircular rod. Now let us consider this to be of a radius r. So length of the straight rod is nothing but 2r, and since this is r, so semicircle area of this semicircular arc would be nothing but pi times r. So these r would get cancelled, and what we would be left with is 2 upon pi. So the rate of heat transfer of semicircular rod to that of straight rod is 2 is to pi. Hence option A is the correct answer. A room is maintained at 20 degrees Celsius by a heater of resistance 20 ohm connected to 200 volt mains. The temperature is uniform throughout the room and heat is transmitted through a glass window of area 1 meter square and thickness 0.2 centimeter. What will be the temperature outside? Given that the thermal conductivity K for the glass is 0.2 calories per meter per degree Celsius per second, and 1 joule is 4.2 calories, or 1 calorie is 4.2 joules. So the options given are 15.24 degrees Celsius, 15 degrees Celsius, 24.15 degrees Celsius, and none of these. So heat developed by the heater H can be V square upon R. So in terms of joules or in terms of calories, so that would be 200 squared upon the resistance of 20 volts, but since we need it in calories, as the unit is given in calories, 1 joule is 4.2 calories. So multiplying this by 4.2, we'll get this value. This is the value of heat developed by the heater. Now heat conducted by the glass. So heat conducted by glass is nothing but equal to 0.2 Ka delta theta upon T. So that is 0.2 into area of 1 meter square. The room temperature is 20 degrees Celsius and the surrounding temperature, let's say theta, upon the thickness of the glass is 0.002. So equating these two, we get 200 squared upon 20 into 4.2 is equals to 0.2 times 1 into 20 minus theta upon 0.002. So solving this for the value of theta, we get the value of theta as 15.24 degrees Celsius. Hence option A is the correct answer. A sphere, a cube, and a thin circular plate, all made of the same material and having the same mass, are initially heated to a temperature of 1000 degrees Celsius. Which of these following will cool first? The options given are plate, sphere, cube, and none of these. As we know, the rate of cooling dq by dt is given by A sigma epsilon T raised to 4 minus T naught raised to 4 upon mc. So this is the rate of cooling, and since the material is same, so the sigma and epsilon and all the properties are similar, so therefore we can say is dq uh, d theta upon T is proportional to the temperature or the area of the objects. So now in these options, the area or the object with the largest area would be the plate. For a given mass, plate would have the largest area. So that would radiate more amount of heat as compared to all the other objects. So hence plate would cool first. So option A is the correct answer. A black metal foil is warmed by radiation from a small sphere at a temperature T and is at a distance d. It is found that the power received by the foil is P. If both the temperature and the distance are doubled, the power received by the foil will be. The options given are 16P, 4P, 2P and P. Now energy received per second, so that is nothing but the power is proportional to T raised to 4 minus T naught raised to 4, that is temperature of the sphere minus temperature of the surrounding. So basically power is proportional to the fourth power of the temperature. Also, energy received per second of power is inversely proportional to the distance or distance squared. So that is also known as the inverse square law. So therefore, power, if we equate these two equations, so power is proportional to the temperature raised to 4 and inversely proportional to the square of the distance. So therefore, P1 upon P2 is nothing but T1 upon T2 raised to 4 times D2 upon D1 squared. So P1 upon P2 is equals to T upon 2T raised to 4 times 2D upon D squared. So this comes out as 1 by 4. So P2 is equals to 4 times P1, or we can say P. So hence option B is the correct answer. One end of a copper rod of length 1 meter and area of cross section 10 raised to minus 3 meter square is immersed in boiling water and the other end in ice. If the coefficient of thermal conductivity of copper is 92 calories per meter second degree Celsius and the latent heat of ice is 8 into 10 raised to 4 calorie per kg, then the amount of ice which will melt in 1 minute is, the options given are 9.2 into 10 raised to minus 3 kg, 8 into 10 raised to minus 3 kg, 6.9 into 10 raised to minus 3 kg and 5.4 into 10 raised to minus 3 kg. Now heat transferred or the amount of heat transferred through the copper rod is given by Ka delta theta upon the length of the copper rod for a given time t. Also, this amount of heat Q is used to melt the ice of mass m having a latent heat L. So equating these two equations, we get Ka delta theta times T upon L is equals to mass of the ice into the latent heat of the ice. So rearranging to get the mass of the ice, we get m is equals to 10 raised to minus 3 into 92 times 100 minus 0. This is the temperature of boiling water and this is that of ice, times 60 seconds or 1 minute upon 1 into 8 into 10 raised to 4. So solving this, the mass of ice we get as 6.9 into 10 raised to minus 3 kg. Hence option C is the correct answer. The figure shows a system of two concentric spheres of radii R1 and R2 and kept at temperatures T1 and T2 respectively. The radial rate of flow of heat in a substance between the two concentric spheres is proportional to, the options given are R1 R2 upon R2 minus R1, R2 minus R1, R2 minus R1 times R1 R2, and ln of R2 upon R1. Now let's look at this diagram. This is a sphere and this is the internal sphere. Now the formula for rate of heat transfer dq by dt is equals to Ka d theta upon the length. But however, in this sphere, at any given radius, the area and the area keeps changing for every radius. So for this radius, the area is pi r x square, so 4 pi r x square, and for let's say another area at a different radius, the area would be different. So therefore, since this is not doesn't have a constant area of cross section in the radial direction, so therefore we need to modify the formula slightly. So dq by dt, let's call it as h, that is the rate of heat transfer, is equals to k times 4 pi r square into dt upon your dr. Here let's consider a point at a radius r, so therefore the area at that radius r would be 4 pi r square, and let us consider a small thickness to find out the area, length at that point. So that small thickness, let it be small thickness of dr. So therefore if we solve this, h is equals to 4 pi k times r square into dt upon dr. So let's rearrange these terms. So what we get is, this would be minus, so minus. So therefore what we get is 1 upon r square into dr is equals to minus 4 pi k upon h times dt. Now integrating both the terms, we get integration of 1 by r square dr is equals to, since all these are constants, so minus 4 pi k upon h integration of dt. This would be from r1 to r2, and this would be from t1 till t2. So therefore this integration is nothing but 1 by r from r1 to r2, or minus 1 by r from r1 to r2 minus 4 pi k upon h times t from t1 to t2. So this would now be 1 upon r1 minus 1 upon r2 is equals to minus 4 pi k upon h times t2 minus t1. So therefore r2 minus r1 upon r1 r2 is equals to 4 pi k upon h times t1 minus t2, taking this negative sign inside. So therefore the value of h now becomes 4 pi k r1 r2 times t1 minus t2 upon r2 minus r1. So let's replace h by dq by dt. So dq by dt is basically proportional to, since all these are constants, so it's finally proportional to r1 r2 upon r2 minus r1. So this is nothing but similar to option A, hence option A is the correct answer. The adjoining diagram shows the spectral energy density distribution E lambda of a black body at two different temperatures. If the areas under the curves are in the ratio 16:1, the value of temperature T is The options given are 32,000 Kelvin, 16,000 Kelvin, 8,000 Kelvin and 4,000 Kelvin. Now in this diagram, as we can see, for the temperature T, the area under the curve would be greater as compared to the temperature of 2000 Kelvin. So area under temperature T upon area under 2000 Kelvin is given in as 16:1. So also now this is a E lambda versus lambda graph, which is nothing but equal to power. So the area under these curves gives us the value of power, and as you know, power is proportional to the fourth power of the temperature. So therefore area under the T temperature T upon area under 2000 is equals to temperature T upon 2000 raised to 4. So 16 upon 1 is equals to T upon 2000 raised to 4. Taking the fourth root, we get 2 upon 1 is equals to T upon 2000. So the value of T comes to 4000 Kelvin, hence option D is the correct answer.